Welcome to Back to Basics for waves, sound and light. You might recall some of the wave basics you need to understand the Doppler effect, but we have to go over some of the calculations and principles again. Remember that waves have some parts that can be measured. Waves are just many cycles occurring over and over again. The length of time it takes to complete a cycle is called the period. The period of a wave is given the symbol t and is measured in seconds, like most other measurements of time. Now, since the period of a single wave isn't all that useful because the numbers tend to be very small, we seldom measure it unless we are looking specifically at one pulse. From the period, we can work out the frequency measured in hertz. That is the number of complete cycles per second. We use the symbol F to represent it. The simplest relationship between period and frequency is this one. The frequency of a wave is equal to 1 divided by the period or vice versa. We can also say that the period is equal to 1 divided by the frequency. The physical distance between complete waves is called the wavelength. It's measured between two parts of waves, one after the other, that are moving in the same way in the same position. The symbol in equations is called lambda. That's a Greek symbol, and it looks like this. The wavelength, like any other physical length, is measured in meters. The wavelength of light, for example, decides what color of light we look at. The wavelength of sound waves decides which pitch we hear. But you might remember that pitch usually refers to frequency of sound and not wavelength. The two are linked. It's pretty important that we quickly revise the wave equation to understand the relationship. It says that any wave's velocity can be worked out using the simple formula of v equals to f times lambda. So velocity is equal to frequency multiplied by the wavelength of waves. This works for sound and for light. The only major difference is the speed. Light moves at over 300 million meters per second, while sound moves at around 340 meters per second, and that depends on the material. So sound is much slower than light. So that means that wavelength can be worked out from frequency as long as we know the speed of the wave. We simply manipulate the wave equation to say that lambda is equal to the speed of the wave divided by the frequency. We can also calculate the frequency of the wave in a similar way. Then the f is equal to the speed of the wave divided by lambda. The relationship between the two is very important. They are inversely proportional, so a high frequency means a shorter wavelength, and a low frequency means a lower wavelength. It is important that you understand these basics before tackling the Doppler equations later in this module.